The objective is to illustrate in 3 segments the mapping Python design methodology, including integration of a GPS map coordinates implemented in an actual global position and engineering prototype as it relates to an intelligent robotic drone. Technology is influencing and improving our way of life, and metaphysics of artificial intelligence is evolving, projecting a new paradigm in the design and development of intelligent platforms, such as the one presented in this video. The objective of this framework is to illustrate an actual engineering prototype model of a cognitive artificial intelligence neuromorphic flight control system. The software platform consists of complex mathematical algorithms and sophisticated software models. Many of these models are developed with Python and C++. The main objective is to provide the control environment for the motor and sensory segments. Here I illustrate an engineering alpha test model of the system. The motor algorithms provide solutions for pulse width modulation by controlling several analog ports. The RPM of the counterclock motor needs to be different from the RPM of the clockwise motor. Pulses are calculated and corrected with firmware for voltage drops. Software and firmware. Set up the software framework and firmware methodology. Includes defining type multi-copter environment by using the config.h, which is essentially the configuration file. Then set up and configure the motor's main throttle and set up the I2C bus interface. Defining the software drivers, including the sensory subsystems such as the gyroscope, the accelerometer, barometer, the GPS, the IMU mathematical software algorithms, including the software libraries. This application illustrates the motor software control mechanisms. The software models which activate the motor movement for the intelligent drone system is created with C++ and Python, integrating solutions for pulse width modulation by controlling several analog ports located in the main computer artificial intelligence digital platform, as illustrated in this video. Other software dependencies for the inertial sensory system contains the mathematical algorithms to enable the gyroscope, the accelerometer, the GPS, the digital compass, and the digital motion sensory systems. They are also included in this methodology and illustrated in this video. The telemetry and airspeed sensor system connects the autopilot to your computer system, allowing to monitor the drone flight, path, and performance while in flight. In addition to flight changes and other flight parameters during the mission, the telemetry info is logged and saved on your system during the flight and events, and the mission planner sets your waypoints and flight location on the map. The GPS application requires a KML, which is a file format used to display geographic data in an Earth browser such as Google Earth. So KML uses a tag-based structure with nested elements and attributes, and is based on the XML standard. Therefore, all tags are case sensitive and must appear exactly as they are listed in the reference document. The reference indicates which tags are optional. Within a given element, tags must appear in the order shown in the reference. Place marks is one of the most commonly used features in Google Earth. It marks a position on the Earth's surface using a yellow push as the icon. The simplest place mark includes point element, which specifies the location of the place mark. So you can specify a name and a custom icon for the place mark, and you can also add other geometry elements to it, as it is illustrated in this example of the code that I have presented in this video. Many different types of paths can be created in Google Earth, and it is easy to be very creative with your data, such as in the KML. A path is created by a line string element, and also I have implemented this element in the Python software algorithm as illustrated in this presentation. The algorithm is used as a general purpose NMEA parser to plot positions on the map as based on this specific application. Calculating GPS latitude, longitude from NMEA strings. GPS module reports coordinates in WGS 84 datum, latitude, longitude in degrees and minute format. There will be two types of coordinate systems: the decimal degrees and degrees, minutes, and seconds. Artificial intelligence drone. For stabilization and orientation, it utilizes a 3x gyroscope and 3x accelerometer. For navigation, it has a magnetometer and a GPS antenna. The system also includes an onboard SD card for data logging. All of this is integrated in a small form factor. I also integrated a telemetry radio and airspeed sensor system. The telemetry radio connects the autopilot system to a laptop computer so you can monitor the drone. In an autonomous mode, the autopilot controls the servos. Inputs from the RC transmitter can outride the autopilot. Now let's talk about the software interface. There are several software models used to program and to monitor the flight. In this case, we use Mission Planner software. First, set the waypoints on the map. Waypoints include setting altitude, speed, and other actions. 2. Load the waypoint to your drone. And 3. Set the roll and pitch and yaw actions. 4. You can switch from manual to autonomous mode. In addition, telemetry logs are recorded and saved automatically on your laptop during each flight and after every flight. The airspeed sensor system allows for control of the drone based on airspeed instead of the ground speed, which comes from the GPS readings. The autopilot is connected between the RC receiver and the control servos.